let's see. So the topic is a few famous limits. So in other words, the ones that we have to remember. The first one comes from the derivative of sine, or vice versa. You know, that limit actually gives us the derivative of sine, but it's based on trigonometry, so we're not going to just be doing it. But there's another one, and that comes from that's the same for cosine, a similar one for cosine. So if we go a limit cosine x minus 1 over x, same idea, almost the same function, but with this negative 1, which still works out this way as limit x goes to 0, cosine x minus cosine 0 x minus 0. So once again, this is the difference quotient, and we have a well, its limit is the derivative. Okay, so this is cosine x prime at x equals 0, okay, which is negative sine at x equals 0, and so the answer is 0. Okay, so that's how the sort of differentiation of trigonometric function starts. Okay, and then so in other words, the fact is that the graph of cosine crosses the x-axis horizontally. Okay, so this is the cosine x. Okay, and then in a similar way, we could convert this this limit into limit of sequences. In the same manner, like this. So you pick xn equal to 1 over n, and then just plug it in. So that is the fundamental relation between limits of functions and limits of sequences, is that you replace each x with a sequence xn, and then it should produce the same limit. So by replacing x with xn, you create a sequence from a function, and then that function, that limit has a sequence, and it should have the same limit as the original function. So that's exactly what happened up there with sine. So I picked any sequence xn should produce the same limit. Okay, and specifically that was the next step, picking sequence xn equal to 1 over n, so that to produce a more specific formula for the limit, and then that since the limit is the same, so we know the answer. And then, well, we right now we just do the same thing for the second limit, so it will be very similar. And cosine 1 over n minus 1 goes to 0 as n goes to infinity. Okay, so so that is not another one limit to remember. The next one is might be even more famous, and that is the limit of this limit 1 plus 1 over n to the n. Have you seen this limit before? You remember what it's equal to? It's actually the number e. Is produced by this limit, and you can interpret, so that makes up a theorem, as a matter of fact. You can actually remember where this comes from. So that expression, what is the meaning of that expression, 1 over n? It is in fact it is a compounded interest formula. Compounded interest, when compounding is happening over the same period of time, but multiple times. So when n is equal to 1, what I have is 1 plus 1 over 1, so it's 2. So double. You double your money in a year, so that's like a 100% annual interest rate. So that's the 1 over here it stands for 100%, and that's how you double your money. Okay. However, you can do more money with the same percentage rate if you compound it twice. You compound it half a year. So the interest is the same, but what's going to happen is I will go with 1 plus, and I'm getting 0.5, 1 over 2, 2. Okay? So in other words, what this is you get 50% the first time, and then 50% the second time. So you multiply by 1.5 twice. So instead of getting 100% at the end of the year once, you get 50% twice, which sounds like the same, but see, because of the compounded interest, that's the magic of compounded interest, you get more money, right? So 1.5, you get that 50% compounds for the rest of the year. Okay, so as you can see, 1.5 times 1.5 is 225. Okay, so same interest rate. So that one is still over here. It's the same one. It stands for 100%, but we divide it in 2. But we replace that. Then that division is accompanied by multiplication, and then the end result is bigger than it was. So we are getting extra 25%. So instead of getting 100% extra at the end of the year, we're getting 125%. Okay, so that's how compounded interest works. And then that's what's happening. What's interesting is, well, what if you do it quarterly and you have 1 plus 1/4 to the 4th power? Okay, and so in other words, 25%, you receive 25 4 times during the year, and then what the end result, I don't remember what that end result is. Well, where's my calculator? Calculator. So what is it? 1.25. 1.25 multiplied by itself 4 times. 2, 3, 4. Okay. So it's approximately, what is it? 244. Okay, so you're not getting 100%, you're getting 144%. And then on and on. So every time you convince your bank to compound your interest more and more and more frequently, you're getting more and more money. The question then is, which is entirely not obvious, is are you going to get the infinite amount of money at the end if you really continue with this process? And the answer is no. Right? So you see how much you're going to get. You're going to get at most, well, when n goes to infinity, you will get E dollars. For $1 at the end of the year, you will get E dollars at best. Okay, so why is it E? Why is it not infinity? Well, we don't know. That's just how it works out. Okay, so that's this another famous limit, and I don't think we have. And then you might remember how that E appears in well, you might remember what this is called. It's called continuously compounded interest. So that's where those continuous models for exponential growth come from. And that's why E as a base is so popular. Well, maybe not. No, that's not why E is so popular. E is popular because it crosses out of all the other bases. Is because it crosses the y-axis at 45 degrees. Okay, but yeah. So you can once you choose to compound continuously. That's what the end result is. Is what happens if you are not compounding it yearly, not quarterly, not daily, not minutely, but every single moment at infinity, so instant continuous compounding is happening, then you will get E dollars for each dollar of your initial investment, and then if your APR is 100%. If it's less, then you have to scale that back as well. And that way you will look at this function ERT is a continuously compounded interest as a function of now becomes a function of base E rather than what is it, base this is a base. You start with a base, say 2. If you are doubling, then your ratio is 2, and after n years you have 2 to the n. Okay, but if you are doing continuously compound interest, that you end up with exponential function base e. Okay, so but we're mostly interested in this limit, so because it will come up. Okay, so well, that mostly these 3 are main important limits. There are limits also from geometry. You know how you build. Well, maybe it's worth mentioning as well, and it is the original method of finding the value of pi. Okay, so once by the ancient Greeks, once they discovered that the length of the circle is proportional to its radius. Yeah. Okay. So they were trying to find what that proportion is, and you might remember how it is done. If they would approximate the circle from the inside as well as from the outside with regular polygons. Okay, and then if I remember correctly here. Well, this is what actually it produces. So as you have more and more, so polygon with n sides. Okay, then as n goes to infinity, is supposed to converge to 2 pi r as n goes to infinity. Okay, so that's supposed to, and that certainly will have to be worked out, considering that they didn't really know limits to begin with, no functions at the time. So, so if this is my r, the radius of my circle, that's another sequence. So functions are important, and the limits of functions are important, but there so much more stuff happening with nothing but sequences, and this is the example. The polygon, what I mean, not the polygon with n sides, but rather what we're talking about is the perimeter. The perimeter of a polygon with n sides, it is supposed to converge as a sequence to 2 pi r. Okay, so the way it works out is really uncomplicated. It actually turns out to be r tangent pi over n times 2n. Okay, so the radius is, this is my radius, and then what's happening here, I figure out the length, which what this is the, no, not this is the length of the side. So this is the length of the side multiplied by, well, maybe this. Okay, then multiply by n, and you have the perimeter. Okay, and then you take the limit, and you end up with 2 pi r, and you can probably guess how this carried out, where this limit comes from. Why is it goes where it goes? Well, because of those 2 limits that we started with, sine and cosine. So sine and that's what tangent is. It's sine over cosine. So you can see how that works out. Anyway, so this is just an example of sequences, and we're gonna continue on a different. We take a different angle at sequences. It's called series, and later on in the semester, and then we're gonna that will reappear on a more different scale when we're gonna have convergence of sequences, of functions, which is more important, and we're going to be talking about approximations of functions for the most part, rather than just some numbers. But at this time we set this aside and looking to start on our way towards multidimensional calculus, and it starts with what's called parametric curves. Specifically, the first topic will be just elementary Newtonian mechanics or motion based on the elementary calculus as was invented by Newton. Okay, so well, just motion that you have seen. Okay, you have seen motion in calculus 1. After all, this is the best, the original and the best metaphor and explanation, interpretation of calculus. So f of x is the location at time x, then f prime of x is the velocity at time x, and then f double prime of x is the acceleration at time x. Okay, and then you can go in reverse, and instead of the differentiation like this, which is really easy, the hard part is that's what really Newton faced, is going backwards. So you know acceleration, where from? You know acceleration from, acceleration is usually in physics known from what? According to Newton, one of the laws of Newton. Remember this one? So, which one is it, second or the first? Well, doesn't matter. So we know acceleration A from the forces. So he was thinking about gravitation, obviously, and if you know the gravitational forces, you can figure out the acceleration. From acceleration, you'll figure out velocity, and from velocity, so through integration, you will find the location. Okay, and that's how he computed the motion of planets. Right? So roughly that's what happens. Except now this is Calc 1, and this is simply does not work. Why? Because it's all one-dimensional. So we cannot, staying one-dimensional, we cannot reproduce anything from what Newton did. And not even planets. What we really care about is simply starting with a simple problem of throwing a ball in the air and figuring out its path. Okay, so same story, unless we're doing this, throwing ball in the air vertically, we need two dimensions. So we're moving horizontally, moving vertically, so we already have two dimensions. Forget about the third dimension. Let's say just it is moving in the vertical plane without deviation. So there is no like a window or maybe spin. It goes straight, but still you need two dimensions. And that's where sooner or later, and better sooner than later, we should start towards a multidimensional calculus. Okay, so then what happens? What happens if we are now moving on to problems that we can actually solve and produce something tangible? Like know where the ball is going to land. If we know its speed and inclination in the beginning, or that all is applicable to ballistics, and that it took them a while actually to figure out how to apply calculus to ballistic. You would think that's should be right there. So the science was there, but they were not able to actually make it usable for at least 100 years. In fact, I looked it up at some point. So during the American Civil War, they were not using calculus for artillery. So to aim the cannons, they simply took them to the range, shot it a few times at angles like 1 degree, 0 degree, 2 degree, 3 or 4 or 5 degrees, and saw how far it went, put it in like a table of this size, and then gave it to every artillery officer. That was it. Both southern and northern armies. So they were probably aware of the ballistics of Newton's how Newton did it, but well, he didn't do artillery, but certainly the physics is there. There's a force. You figure out, you get the acceleration, you get the velocity, and then you get the location. But it's just turned out to be more difficult than you'd think to translate that language from science, a piece of paper, to actually to the field, what's happening in the field. And you can look at those cannons. They only had like well, those tables, you can find them online. The table, range table, just very small set of numbers, and the inclination that they were willing to consider were like I said, 5 angles, 5 degrees variation from 0 to 5 degrees. That's all. And you can see it markings on the cannons. So like this. And so you can turn it up and down a little bit, but not a lot. So anything shooting maybe any angle that's bigger than that would not be considered any kind of accurate shooting. So shooting over an obstacle or anything over your own troops, all of that pretty much was out of the question just yet. So it took but only by the end of the century, I think it was finally became a commonplace. So anyway, so what do we do to move in that direction? We're going to need 3 variables. So, and they are the switches is that you have to look. You have to. It's not x and y anymore. So we make t time x horizontal location and y vertical location. Okay, so then these are the latter two. The latter two are the dependent variables. 2 dependent variables, and this is the independent variable. Okay, so that's the big deal that changes. That has changed is that instead of having one dependent variable, we have now 2 dependent variables. But there's nothing tricky is going on. The x depends on t, y depends on t. The end. If you think about it, that's what you expect from motion. It is moving in time, in space, and so you can say that well, the location depends on time. Okay, so location. So these depend on time. So that way you can say x is equal to say f of t, y equal g of t. Okay, and then there is really no trouble for us to repeat this idea. That does not change. That does not change. The only thing that might require some kind of more physics thinking than mathematical thinking is that x and y are not dependent on each other. So that might be questioned somehow, but really it is if you know time, you know location, you know x and y, and so that is a functional relation of location on time. Except we now have 2 functions. 2 functions that have nothing to do with each other, because once again that's kind of physics. Idea here is that horizontal motion. So it's like you're looking at the motion, and maybe like this, and then you can look at it in 2 ways. So that's what an observer sees, but you can imagine that, okay, so there could be 2 observers, and they say one like this, standing like this, and the actual maybe the gunner, so it's standing behind the cannon, and then he only sees, what does he see? He only sees up and down, like this. So he sees he sees wise. It goes up only. He does not see really without, unless there is some kind of perspective idea. If you can pull it off, then you can only see how the cannonball goes up and then it goes down. Okay, so that's your function y. And on the other hand, who sees the x-axis? Maybe somebody is lying like this on the ground. Okay, so that person will see motion x. So it will only see the horizontal motion. So that's x. So that's kind of a decomposition of motion, which comes from nowhere in a sense, because when you do shooting, there are no axes for us to worry about. So you have to introduce this Cartesian system. Let's face it, this is what we're talking about, into the system, so that we can analyze x's and y separately. And we choose x and y separately for a good reason, because they behave very differently, or the physics is very different for x's and y's. So there is no trouble for us to choose x and y this way. Why not? It's, like I said, there is no, you don't see any x's out there. So we choose x and y, one horizontal, one vertical, so we simply aligning y with what? With gravitation. Okay, so Gravitation is pointing in a particular direction, so let's align y with the gravitation, except usually it's in the opposite direction. So gravitation is pulling down, and y is pointing up. But other than that, we break our motion into separate components, and then we can analyze them entirely separately, and that plan that we have outlined from Calculus 1 will be fully applicable. So either we know our location, we find the horizontal location first. You have a horizontal location f, then you go on, you find its derivative f prime, you find that derivative of that f double prime, and then then you have location, velocity, acceleration. Okay. Similarly, you do it in exactly the same manner. You differentiate the g, the vertical location, and once again you have derivative, vertical velocity, second derivative, vertical acceleration, and then these can be analyzed. And once again, if you that plan over there is still applicable if we have the forces are known. If the forces are known, then we can derive the acceleration for x and y. For x, so f double prime, y double prime will be known, and then we retrace our steps. Only instead of having one list of steps that for f we have one for f and one for g. Okay, and then that way we figure out where the location. So let's just carry out one plan for that. So the simplest possible situation that is familiar to us. So we're gonna, well, the simplest situation is, well, what are the forces first? Okay, so once again, the vertical and horizontal. So suppose m is known, so that way we can proceed from this to acceleration right away. But we need to know the forces. So what are the forces affecting an object, a cannonball flying through the air? Gravity. Okay. What else? So it's vertical, and acceleration is g, which is 32 feet per second squared. Okay, except it will be negative, right? So it's negative. G is just the positive part. So any other vertical forces? Assuming that it's in the vacuum, so we don't want to deal with air resistance. What about horizontal? Once again, no air resistance. Are there any forces horizontal? No? Yes? So I'm not sure if you gotta supposed to recall something from physics class or just common sense. The common sense might be tricky because you gotta actually explain to yourself what is the meaning of the forces. So we're using that very casually, whatever that is. But we are talking about so from the mathematics point of view, then it is probably easier to think in these terms, in terms of acceleration. So is there, in a horizontal direction, is there any, is there an acceleration, horizontal acceleration, or deceleration? No? Yes?
Is it from like the work, from like when we, like if we were talking about like a cannonball, like where we shoot it out, it's like
yeah.
the work and the horizontal axis as well.
The work?
Yeah, like the force moving it horizontally coming from the cannon.
Yeah, well, if there is a force, then it does do some work, but is there a force? In the whole situation, there is the gravity, yes. Is there any other force? Well, the end simply there isn't. So once again, to explain why you cannot do it from the point of view of mathematics, I guess the best way to think about it is just skip over that question and then assume just put it this way. Probably Newton did it exactly that way. Let's see. Suppose there is nothing but gravity. What would be the motion of the ball, of the cannonball? Okay, so maybe if it doesn't work out, we'll know that there is something else. Okay, we know that it will work out, and so that would provide evidence that there are no other forces. Okay, so that's kind of a roundabout way, but if you don't want to make assumptions and you don't want to really try to figure out what is the meaning of the force is, well, let's say, let's just take one force that we know is there and then just run with it, and then we confirm that things work out. We will see what we see in the field. We're gonna produce the mathematics that very much resembles that, minus the air resistance. Okay, so let's do that. So gravity is force is g. So then the F is equal to mg. Okay, so then well, we know we don't need mass. You right away discover that really mass does matter, right? Because we do need acceleration. So why do we need it? Why do we need a force to begin with? Just go straight to acceleration. So then F double prime is equal to negative g. Okay, so that's our equation. So that equation describes everything about our vertical motion. With we would be missing data would be the beginning, the velocity, the initial position and the initial velocity. But other than that, we are very good. So F prime moving backwards. So this is acceleration. We're moving to velocity. So what do we get? How do we get the first derivative from the second derivative? Well, the second derivative is the derivative of the first derivative. So we need to reverse. How do we reverse?
On the antiderivative?
Yeah, so in other words, integral. So we take F double prime dx, and so we'll have integral negative g dx. I'm sorry, that's not x anymore, it's a t. So it will be negative gt plus c, right? So that's the antiderivative. Not just one antiderivative, but a bunch of antiderivatives. So each c provides a new antiderivative. The meaning of that extra c is important. It means that the same acceleration might produce different patterns of velocities, even though they are very closely related, right? Look at it. It's just it's a linear function, right? It's a linear function. Negative g plus c is a linear function, and they differ by a constant. Okay, so just shifting those lines, or rather lines like this. The slope is negative g. And you switch it by c as you move along. So in other words, if you only know acceleration, then you don't know everything yet. There is a lot of variability left to it, and that's what provided by c. You narrow it down if necessary, and there is a particular meaning because c is in fact f prime of 0. Right? Look at it. So f prime of t is equal to negative dt plus c, so which means that c is the value of that function at 0, and it is then justifiably called the initial velocity. Initial meaning that at time t equals 0, even though it doesn't have to be start at time t equals 0. Your motion might start at a different moment of time, but that's fine. Just as well, could be 0. So that's the meaning of C. And then we don't stop here, because at this point, even if we identify the initial velocity by, if it's a cannonball, and then how do you know initial velocity? That takes out, by the way, some experimentation to find out your muzzle velocity is what we're talking about. So how fast it is leaving. Well, the muzzle velocity will give you the velocity that is unrelated to the angle of your cannon, where you're pointing. So you'll still have to split it between x and y. So we'll get to that. But that's initial vertical velocity. That's the initial vertical velocity, and then we don't stop here. We actually interested in location. So what do? We integrate it one more time to get f. You integrate f prime. Okay, so it's negative gt plus c dt. As you can see, after you start with a constant, you integrate once, you have a linear function. You integrate twice. What kind of function do you get? You got a quadratic. Okay, so negative gt squared over 2 plus ct plus, say, k. Okay, so you integrate. C is unspecified. G is specified. We know what it is, even though you can certainly change g to any other number. If you go to another planet, that will work out just as well. You got to just change the value of g. Okay, so C is also known. It is in our power to know what the initial velocity is. And then look at it. It's the same story. We want to figure out the meaning of K, which gives us shifts. A bunch of parabolas are the answers. Well, in this particular case, the parabolas, since G is positive, these bunch of parabolas will be upside down. Okay, they are identical parabolas. Switch that plus K only moves this thing up and down. And what? And then the meaning of K is, just as before, K is equal to f prime of 0. So it is the initial initial vertical location. The initial vertical location, so in other words, from what elevation you are shooting. So maybe it is you have a cannon on the hill, and you're shooting maybe it doesn't matter, it could be forward or not, that doesn't matter, but this will be your trajectory. Okay, and then this is K. This is K. So elevation above the 0, whatever. It certainly is variable and depend on our x is our choice. So then K is also our choice. But once it's chosen, then both K and C are known. Okay, so that does it as far as the vertical is concerned. So we have a specific formula that fully describes vertical motion, which incidentally you can still have nothing but vertical motion. If you're just shooting in the vertical direction or throw a ball directly in the vertical direction, then you ignore the horizontal direction altogether, and then this is the solution to the problem, which is really with nothing but the tools of calculus 1, we solve the problem completely. So depending on all you need, what's missing is simply the initial location and initial velocity. Okay, and then you know f as a function of t. So for every t, you will know your elevation or the altitude of the cannonball, and then you can answer questions such as, for example, how long it is going to be staying in the air, how long it will take for it to reach the highest elevation, what is the highest elevation, how hard it's going to hit the ground. All of these questions will be known. All you need to know is they can be derived through nothing but algebra from this formula. So solving equations, for example, when is it equal to 0? When it hits the ground, it is when this whole thing is equal to 0. So solve equation. What kind of equation? Quadratic equation, you can do it. Okay, so that question can be easily answered. You can also, it is a parabola upside down, so you know how to find the maximum value of parabola. So once again, if the formula is given, you can find it easily. If you are interested also in the certain velocities, particular moments of time, then the previous formula might also come into play. Okay, but otherwise you don't have to differentiate again. You already have it. Okay, so that solves the half of the physics problem, and we do indeed have to do it because that trajectory that I plotted over there is really very well, everybody knows that is a parabola, but it's not the same parabola as what we are just built, right? So this is a parabola, but this is a function of x as a function, y as a function of t. That's what we have found. This one is a function of y as it depends on x. So in other words, we would not have this picture unless there is some horizontal component to your motion. So, well, you just progress from vertical to horizontal. Okay, things are way simpler because there is no force. But the plan is the same, so we just have acceleration, which is 0. F double prime is 0 this time. Okay, so it only makes our life easier. Anti-differentiation will be easy. So we get velocity, which happens to be not linear anymore, but rather what? It is constant, right? So all of these things that we learn about in the kind of abstract setting in Calculus 1 now become very specific, tell us something very specific about motion. So 0 acceleration gives us constant velocity. On the other hand, constant acceleration gives us linear velocity, and so on. So this one will be simply, say, okay, a constant. So velocity is constant. So if you think about it, it might seem a bit surprising, considering that picture on the right, but it is progressing. The cannonball is progressing in the horizontal direction at a constant rate. Okay, this certainly was not, I'm not sure, probably was not taken well, because you do know that it does slow down, and the trajectory is not a parabola, in fact, but because of the air resistance, it slows down. So that, starting with Newton himself, he tried to sort that out, dealing what to do with air resistance and how to match the real life shooting better than this. So we'll get to that later. At this point, let's just solve this problem at its simplest. So this is shooting in the vacuum. So what is the meaning of m? M is equal to f prime of 0. So once again, the analysis tells us the same, that this is the initial horizontal velocity. Okay, so in fact, if it is you're shooting a cannon from elevation, you might choose to have 0 elevation. I'm sorry, you might choose to have 0 inclination of your cannon. So you can shoot straight forward the horizontal direction. So it is possible that that's not f. I'm sorry. Yeah, I called them g. So I called the other function g. So let me stick with that. So this is g prime, g of 0. That's not the same g though. Not the same g. Okay, so there might be f prime of 0 might be 0. There is no vertical component to our shot, but there's the whole thing goes into horizontal velocity. So and then we got location, and we know that what's going to happen when we integrate a constant function, it's going to be linear. So n, once again, is a constant. We have a linear function. So certainly simpler than the last one when it was quadratic, but it is still makes the picture complete. So where n is equal to g prime of g of 0, it is the initial horizontal location. Okay, so well that's it. So I can mark it this. So these two, what I circled in green, are the two functions getting us the motion in the horizontal and vertical directions. And as you can see, there is no relation. Those two constant are four constants have nothing to do with each other. What they have in common is t. So for each t, you have g gives you how far you progress horizontally, and you have f for the vertical progress. Okay, so then it's really no trouble to make it more specific. So for example, I could choose anything specific here. So these four quantities can be made specific. So I want to consider this. So suppose we have a 200 feet elevation. Okay, from when the shot was made, and we are fire horizontally at 200 feet per second. Okay, so that's the situation that is certainly made up, but at the same time is totally realistic. So we have some kind of hill of elevation of 200, and then my cannon is at the top, and we are firing at 200 feet per second over here in the strictly horizontal direction. So this is the hill, some kind. So this is 200 feet is the elevation, and that's the shot. So we want to figure out what's going to happen to the cannonball. So at some point it certainly will hit the ground. We'll see if it matches roughly what we want to what we expect. And okay, we just take this data and figure out those constants. The constants are right there, c and k, initial velocity, vertical velocity, vertical location, as well as m and n, same for the horizontal. So let me go with vertical first. Vertical, horizontal. Okay, so and then I'll have here velocity, location. Okay, so vertical velocity is 0, and I'm talking about initial, right? Initial. So these are initial conditions that are supposed to give us everything. So because there is no change in the physics of the situation, the force remains the same. So the initial conditions will give us everything that's happening. Okay, so the vertical velocity is 0, but the location vertical is 200, right? Okay, and then the horizontal velocity is 200, but that is by our choice, by the way. So let's not ignore that step that I implicitly made. So I added the Cartesian system, which was entirely my choice. So we only know that there was 200 feet elevation above the sea level, so it was our choice to have the sea level at 0 and then measure everything in feet. Well, that's I guess not a big much of a choice, but for example, the 0 horizontal 0 was our choice to put right under the cannon. Okay, so then so then the initial location is 0. Okay, so once again, that's the good news, that even though the amount of work doubled, you do one for x and one for y, but other than that, everything is quite predictable. So what is it? F of t is equal to negative gt squared over 2 plus 200, and g of t is what is it? 200t. That's it. Problem solved. Okay, so we'll just see you next week.